Hello, everyone. Thanks for attending my session. My name is Jian Gao, a PhD student at UCLA and School of Management. Today, I'm going to introduce our paper, Human AI Interactions and the Society Pitfalls. This is joint work with my advisors, Francisco, who is also from Anderson School of Management, and Sebastien, who is from Kellogg School of Management. So let's start with some backgrounds. As we know, generative artificial intelligence has improved at a very rapid pace. For example, ChatGPT recently showcased its advanced capacity to perform complex tasks and human-like behaviors, reaching 100 million users within 2 months after its launch in 2022. And in August 2023, there are already 180 million active users and 1,400 million visits during that month. And this progress is not limited to text generation, as demonstrated by other AI, such as Midjourney, a text-to-image AI, and GitHub Copilot, an AI pair programmer that can auto-complete your code. So we can see we have various AIs that can complete many different tasks. It can answer questions, it can explore something you don't know, so on and so forth. And in this research, we focus on a specific scenario where we use this AI to boost our productivity. So according to a study from Nielsen Norman Group, AI can improve employees' productivity by 66% on average, especially for the tasks that are more repetitive and value speed, such as writing documents and programming, whose productivity can be improved by 65% and 125% respectively. And data coming from GitHub Copilot also confirms this productivity enhancement in the programming tasks. And as I said, what we focus is a scenario where we know how to do the work without using AI, but we try to use AI to make everything faster. So for example, as a PhD student, I usually have lots of coding work to do in my research. With the emergence of these generative AIs, I can get everything in just a few seconds. So in this figure, I try to ask GitHub Copilot to generate some function for some purpose. The initial output is actually functional, so it works, but I don't like it. I think this is too long, so I have to send one more prompt to make my output shorter. And then if I'm still not satisfied, for example, I may not prefer this, I don't like this usage of high function in this equality, then I have sent another prompt to directly ask what I want, okay? And the final output will be more aligned with my personal preference. However, if I do it without AI, I can just finish everything in a single line, which will be much more aligned with my preference. So you can see aligning AI's output with my personal preference can take time, and a rational user like me may have to take the initial output if I'm under time pressure. So for example, if I have a deadline in just a few minutes, then I don't care what I prefer. I would just accept whatever the AI says as long as it works, right? So here it is a trade-off. Either I want a high fidelity of output, pushing the AI output to better match our style or our preference, or I want to save my communication costs so that I can be more productive. And the decision here is how much information I should share with AI. So like how many prompts I should send, or how detailed prompt should be. Sending more information can potentially improve the fidelity of output, but it will also incur a higher communication cost because I need to spend more effort and more time to refine these more detailed prompts. Right? And the major research question we want to answer here is, what are the potential societal consequences we may have when users rationally interact with AI? So if everyone makes a rational decision, what kind of aggregate level consequences we may have at the end? All right, so as a preview, in this research, we consider 2 types of societal issues. The first one is homogenization issue. Because of the communication cost, users may not be able to share full information with the AI, but let the AI choose for us. So in this case, the produced content may lose our idiosyncrasies and diversity and become more and more similar and alike. And the second issue we're going to discuss is AI bias. We know all AI systems have some bias to some extent. For example, we know ChatGPT has been trained by using reinforcement learning from human feedback, where human reviewers can subjectively grade AI outputs. But we know humans inevitably have some biases and leading to some biases in the AI system. So if users cannot share enough information with the AI, then the final outputs may perpetuate these AI biases. So in terms of literature review, our paper is related with some recent modeling studies about human AI interactions in operations management, and also related with some empirical work about generative AIs or issues of homogenization and bias issue. And in terms of modeling approach, we share some similarity with information design, costly persuasion, and rational intention. Compared with these studies, we approach this question from a different angle and attempt to foreshadow how our lives may change due to people's rational decision-making when interacting with AI. So basically, in the last part, I briefly introduced the background. So in the following part, I'm going to talk about the main course today, which is the Bayesian model we built to illustrate insights. Okay. So in this model, we use data to denote a one-dimensional user preference for some specific task, which is normally distributed in population. So for example, for the example about coding I just mentioned, then this data may represent a user's preference on time efficiency versus the memory efficiency. So if I have a data that is on the right, then it means I'm more inclined to improve time efficiency than the average people. And the distance between this data and the mean of the preference mu theta is called the uniqueness of preference. Basically, the more distant from the average, the more unique the preference is. And on the other hand, the AI also has its own prior about the people's preference. And initially, we assume this AI is well-trained. So basically, it means this AI's prior is the same with the population distribution of data. But we will relax this assumption when we talk about AI bias. And then we model the interaction between the user and then AI as an exchange of information. So basically, the user can share some information about her preference by sending a noisy signal queue. So you can consider this queue as the prompt you send, or any words you type, or any signal or any information you share with the AI. And then this is a noisy signal. So we have a variance sigma q. This is the user's decision and controls the precision of this signal. So basically, if I decrease this sigma q, then it is more likely to send a more precise signal that is closer to what I want. It is closer to my true preference theta. But if I increase the sigma q, then it is more likely to send a noisy signal that is far from my preference theta. And then after receiving this signal, the AI will update its prior and generate an output theta A. So this theta A is something with previous content or generated content from the AI, which minimizes the mean square error between the output and the true preference from AI's perspective. So basically, this is the best guess for the AI, giving the information shared from the user. And mathematically, we can express this theta A as a weighted average between the signal Q and the prior mean mu theta. And then let me explain the trade-off of the user. So basically, as I mentioned, if I decrease the sigma q, it is more likely to send a precise signal. And theta A, the output, will get closer to this signal q, potentially reducing the fidelity error, which is defined as the distance between the true preference theta and output theta A. But in the meantime, I will incur a higher communication cost because we have to spend more time and effort refining more detailed prompts to contain more information. So we will have a higher communication cost. So if I increase this sigma q, then it is more likely to generate a noisy signal, and the output theta A will get closer to the prior mean mu theta, potentially increasing the fidelity error, but it will also lower my communication cost. So mathematically, the user will incur an expected fidelity error, which is the mean square error between the output and my true preference theta, conditional on my preference theta, because we assume user knows their preference. And she will also incur a communication cost, which is this I of sigma q. And this is also the mutual information. And H here is the differential entropy. So basically, intuitively, this measures the amount of information that the user shares with the AI. So basically, how many prompts you send or how detailed prompt it is. And then the utility loss is the summation of fidelity error and a constant gamma times the communication cost. So and the goal of the user is to find the optimal sigma q to minimize my communication cost. And here I want to emphasize the meaning of this gamma here, which controls the trade-off between the fidelity and your communication cost. we will refer to it the cost of human AI interaction. So intuitively, a task may have a low gamma if it is particularly easy to use this AI. So for example, we know ChatGPT now has a feature of voice recognition so that you can just talk to the AI and you don't have to type any words by using keyboards. And in this case, it is more convenient to use this AI and you have a lower gamma. On the other hand, a task may have a high gamma if you are under time pressure or if you don't have enough motivation to keep fidelity. So for example, if I have a deadline in a few minutes, then I just want to finish everything as soon as possible, I will have a high gamma as well. And finally, we also assume people can choose to work without AI. And in this case, we assume they can just do the work by themselves with zero fidelity error. So it means we assume these users are experienced. So as I said, so they know how to do the work without using AI, but they just want to use AI to make everything faster because manual work can take some time. And here we assume there exists a fixed utility cost, which is this capital gamma, if they decide to do the work by themselves. So finally, if the utility loss of using AI is less than this capital gamma, then the user will decide to use AI. And the final output, theta star, is just the output of AI, theta A. And the final utility loss is just the utility loss of using AI. Otherwise, they will not choose to use AI, and final output is just theta, and the final utility loss is just this capital gamma. All right. So in the last part, I just briefly introduced the model, and then I will introduce the main results from this model. But before I continue, any questions about the model or the introduction? Yes.
Clarification. So you're assuming this user pays no costs to evaluate the fidelity?
Yes. Yes. So basically, we assume just for example, we just observe the generated content, and we know how different compare with my personal preference. Yeah. So there's no cost for the comparison. Yeah.
Okay, but if I can evaluate it that quickly, presumably it's not that hard a task, and I could generate it with almost no cost, right?
Yeah, that's a good question. That's a good question. Yeah, I think there's a way to also incorporate this cost in the communication cost as well. Yeah. Yeah. Thank you. This is a good question. All right, let me continue. So in the first theorem, we show that the variance of the AI outputs is lower than the variance of original people's preference. So this means the misalignment between AI outputs and a user's preference can lead to a homogenization issue, where the diversity of AI outputs will be reduced. So the produced content will become more similar and alike. So as we can see, the variance of AI outputs is always lower than 1, which is the variance of original preferences. And this result also proves that facilitating human AI interactions can encourage users to share more information and limiting this homogenization issue and preserving the diversity. As we can see, the variance will be higher when the cost of human AI interaction is lower. And when the gamma is finite, and the cost of human AI interaction is larger and larger, more and more people will abandon the AI and do the work by themselves, partially recovering the diversity of outputs. However, the diversity is always lower than the diversity of original preferences because there are always some users who choose AI outputs. So this is the first theorem, homogenization. And as more and more content becomes AI generated, this content can be reused to train the next generation of AI. So for example, we know most of training data of ChatGPT comes from the internet, but if the internet is full of this kind of AI generated content, then we can use this AI generated content to train the next generation of ChatGPT. And we studied this situation within our model by using a self-training loop. So essentially, in this self-training loop, at the beginning, we have some users, and this user decide optimal sigma q, the precision of signal, and they send some signal to AI model, and the AI will generate some output theta star. And then this theta star will become training data for the next generation of AI. So essentially, within our model, this means the distribution of theta star will replace the AI's prior in the next iteration. And then the users will learn the new AI prior and make new decision on sigma q star and send some new signals to the AI model, so on and so forth. So we call it a self-training loop. We simulate this self-training loop to illustrate our insights. And as see, as what we can see in this figure, while the distribution of original preference remains unchanged, which is in blue, the distribution of AI outputs converges to the center. So it becomes more and more homogenized. So it is in orange. This is because when AI supplier becomes more and more erroneous, it is harder and harder for users to reduce the fidelity error. So eventually, it converges to a completely homogenized world where the variance converges to 0. So this means in a self-tuning loop, users' rational decision-making and AI's training process can mutually reinforce each other, leading to a homogenization death spiral. Nonetheless, it also shows that facilitating human AI interactions can also slow down this process. As we can see, the curve with smaller gamma is above the other curves. So this means the variance with lower cost of human AI interaction it will be larger in each iteration. So this is about homogenization. And then, let me briefly introduce the bias part. So in the bias part, we model the AI bias as an AI prior that cannot precisely reflect the population distribution of data. So basically, what the AI understands is not the true distribution of people's preference. So this there's a misalignment. And then we consider two types of bias. The first one is directional bias, where mu A is not equal to mu theta. So for example, we know some empirical work showing that ChatGPT is politically left-leaning. And in this case, ChatGPT may have a directional bias. On the other hand, we're also considering censoring bias, where sigma A is less than sigma theta. So for example, we know for some AI, the training data is censored to exclude some more uncommon cases and unique cases, and only focus on the majority, the mainstream. So in this case, the AI prior is more concentrated on the average on the center. Okay, so this proposition discusses the aggregate level consequences of censoring bias on the whole population. So basically, this proposition and this figure shows that it is better for the whole population to have a more diverse training data set than some censored data set. As we can see, the population utility loss is minimized as some AI prior variance that is larger than 1, and 1 is the variance of original preferences. So this means this result may seem a little bit counterintuitive because we may assume the majority would benefit from the censorship because censorship will make the AI more focused on the mainstream. However, what we found, as shown in this red plot, is that when we increase this AI prior variance, a large group of people would benefit, will be better off because they can save lots of communication costs when interacting with AI. So this means even if censorship can be helpful in preventing dangerous or illegal content, it is very important to train the AI model on a data set that can reflect a wider range of preferences. And this is my final theorem. So basically, this theorem discusses the relationship between AI bias and societal bias, defined as the distance between the average output and the true mean of preference. So basically, it shows that any AI directional bias can lead to some societal bias. So we can see the societal bias is always positive as long as the cost of human AI interaction is positive. And it also shows that improving human AI interactions can partially prevent AI bias from becoming biased because users will be more willing to share more information to preserve their original ideas and correct the AI bias. All right. To sum up, I think the main message from this work is that with the existence of generative AIs, we may have this kind of societal issues of homogenization and bias. And this is not because of the AI itself, but because of our choices, because of our users' rational decisions. Okay, so to mitigate this issue, we need to facilitate human AI interactions to encourage users to share more information and make more effort. All right, so this is the end of my presentation. Thank you so much. Thank you for your attention, and